There are 3 billion rungs on the famous double helix of our DNA. And the code that's involved is a digital error-correcting code. Now, there's not probably one engineer in a dozen that can design an error-detecting code properly. There's certainly a lot fewer than them that can design a code that automatically corrects its own errors. There are such codes, by the way. Most of us are familiar with the 7 or 8 bits that we make to a typewriter stroke called the ASCII codes. If you're, instead of 8 codes, if you're willing to add 3 bits to that, make it 11, you can make it an error-correcting code. There's a computer, NFSQ27, that was built around that technology. You take someone on a tour, and while it's running, you could pull a card out while it's running, and it would go on unheeded because it would correct its own errors to a certain limit. And anyway, we have that kind of code designed in our DNA. It's one of the most advanced language designs possible. And it's the same design that occurs in all life. That implies whoever created us created the plants and the flowers and the animals and whatever, because they all use the same code. Wow. There are simplex alphabets, there are error detecting codes, there are error correcting codes. There's adaptive coding scheme. That's where the codes then will modify themselves depending on the context. And we have all of that going on here. We have the DNA, which is the master blueprint. You have a factory inside you. In fact, in every one of your cells, that factory has a master blueprint file place. And when it needs a copy of this, it transcribes a copy of what it needs and then translates that into proteins. The proteins make up the machines. The machines are the machines that handle all this stuff. Now, there's an interesting question that rises here. Which came first? The proteins need those machines to be made, proteins, and yet it takes the proteins to make the machines. 100,000 different kinds, by the way. Which came first, the proteins or the machines? It's the old chicken and egg situation. You can't have one without the other. They both have to be simultaneously designed, by the way. And we could go on and on about this sort of thing. Amino acids. There are hundreds of different kinds that are known, but only 20 are used by living systems. And they're used to construct the proteins that make us up. It's interesting, when you put one of these molecules together, you can put it together 2 ways. You can build a molecule and you can make its mirror image. It turns out that all living things are left-handed. Right-handed equivalents are poisonous to the left-handed ones. All life uses left-handed chirality. The chirality is always left-handed. Now, there's an insight here that we can easily, if this all happened by chance, if somehow cosmic forces cause these things to happen, you'd get half and half, wouldn't you? Half right-handed, left-handed. No, only the left-handed lead to life. So it tells you it can't be random. It had to be selective, you see. But we'll move on here. Now, most proteins in your body are a link of not 347 like this is, but are up to 500 acids long. Some of them are soluble in water. Some are not soluble in water. They're designed that way. And these amino acids can be combined to make 20 different, some of these are nonpolar, some are polar, some are basic, some are acidic. They have certain, they have these chemical aspects to them. And so they have a common structure that allows them to link into a chain, but each one has its own defining characteristics for what it's designed to be. And we have, of these nucleic acids, we've got 4. And rather than mispronounce all the names, I'll just call them A, T, G, C. And when they're copied in the working version for the factory floor, they're copied in a way, and I've color-coded this just to represent those. It's simpler to read. They're designed in such a way that the A's and the T's always link, the G's and the C's always link, and because they have an affinity for each other that way, it turns out the code turns out to be intrinsically self-replicating. It's as if the original is its own carbon paper, if you will. And so when called upon, they will split, replicate themselves, make a copy of themselves, and these complementary pairs, it's intrinsically self-replicating. So we not only have a complex coding system here, it's one that intrinsically multiplies itself when necessary. Now, and there's a sentence structure implied to this. I won't get into all that here for this discussion. But something else goes on that you need to be aware of. Your DNA has certain, they have a sequence of these codes. You make a copy of them for the RNS for the factory floor to start using these things. Machinery comes by and takes certain portions of that out, and the introns are taken out, the exons, as they call it, are then connected. In other words, these things are edited by the chemical machinery to fit the needs. I want you to remember this because we see the same thing going on in the biblical text. It's called an equidistant letter sequence. And I'll show you some of those in the second session. But this is the messenger RNA, as they call it. It's now ready for replication. And so you have the DNA has been copied, slight change in one of the elements in terms of the alphabet, but that's just the way it operated here. And with these three letters, you can define any one of the nucleotides. Now, the genetic code is simply the alignment of those three-letter abbreviations for each of the different things. There's even punctuation defined in the code, start and stop bits and so forth. Now, the messenger RNA then is met by a protein machine that will transfer that, and as it goes along, it reads like a recording head. It starts and it goes along and copies the codes which generate the elements of the protein chain that it needs. This is all a machine that not only operates, corrects its errors, it also reproduces itself. And we could go on, we could spend the whole evening on this, of course, but those that are negatively charged, they associate with positively charged. Those that are non-soluble in water stack. The hydrophobic ones stack in the center. The ones that like the water are on the outside when they're in contact with water and so forth. And the final stable, the thing that then takes a three-dimensional shape that's appropriate for the tool that is designed to be. And it's all designed by the specific codes. And so, now let's just take one example, and I'm going to pick hemoglobin. Hemoglobin is obviously an element of your blood. It happens to take 574 amino acids in length to make one. And these are the numbers. You have 36 of those and 60. I won't mispronounce all these to go through, but there's 574 in total, okay? Now the question is, they have to be in a specific order. If they're not in a specific order, it's called hemoglobinopathy. It can be deadly. And so this is called specificity, and there's a formula for producing this. It turns out that if you have a code not of 2 but of 20, and you got 574 pieces you need in a row, that'll turn out to the number of possible arrangements you could have is 10 with 650 zeros after it. Are you going to leave that to chance? Heavens no. If you got the wrong one, you got death on your hands. And so only one of them is hemoglobin. And if you change just one of them, you have hemoglobinopathy, or death, if you will. Now, chance itself is pretty inefficient. Say this just happened by evolution, just randomness. Well, the probability of random chance of 347 beads are black and white, we said was 10 with 104 zeros after it, right? A hemoglobin molecule, 574 elements from an alphabet, not of 2, of 20. There's 10 to the 650th power permutations possible. Only one of them is hemoglobin. And if you miss it, you die. Heavy stuff. Remember Borel's law, anything with more than 50 zeros is defined as absurd. Hemoglobin to happen randomly is more than, is really, really, really absurd. Just as is my little example with these silly little beads, okay? That make it 11, you can make it an error-correcting code. There's a computer, NFSQ27, that was built around that technology. You take someone on a tour, and while it's running, you pull a card out while it's running, and it would go on unheeded, because it would correct its own errors to a certain limit. And anyway, there are 3 billion rungs on the famous double helix of our DNA. And the code that's involved is a digital error-correcting code. Now, there's not probably one engine, complex alphabets, there are error-detecting codes, there are error-correcting codes. There's adaptive coding scheme. That's where the codes then will modify themselves depending on the context. And we have all of that going on here. We have the DNA, which is the master blueprint. You have a factory inside you. In fact, in every one of your cells, that factory has an error in a dozen that can design an error-detecting code properly. There's certainly a lot fewer than them that can design a code that automatically corrects its own errors. There are such codes, by the way. Most of us are familiar with the 7 or 8 bits that we make to a typewriter stroke called the ASCII codes. Instead of 8 codes, if you're willing to add 3 bits to them, we have that kind of code designed in our DNA. It's one of the most advanced language designs possible. And it's the same design that occurs in all life. That implies whoever created us created the plants and the flowers and the animals and whatever, because they all use the same code. Wow. There are simple